We own folders.com, labels.com, envelopes.com, a lot of sort of stuff in the printing industry we kind of work with in sort of direct to print, business to business, that sort of realm. I now own a house in Denver, Colorado as of February this year. Woohoo, round of applause for 6.5% interest rates. Clearly software better support me because my financial literacy will not. That is 100%. For me at the interest rates, it's not happening. I also do that one van thing, and that one van thing is 2 years ago I decided I wanted to live in a van, and so I went out and I purchased a 2023 Ford Transit, and I converted it myself, and I kind of got Starlink and sort of worked on the road doing programming and hiking, climbing, that sort of stuff. I'm a big avid nature lover. I love doing all the stuff. Digital nomad, that is 100% correct. It's sort of been my it's my whole personality. Let's just run with that. I do keep energy crystal at my desks. And it's not even a matter of like I'm fully invested into this stuff. It's just a matter of I'm not willing to run any risk. And so with my focus, I use Tiger's Eye, and with tranquility, I use Amethyst. It's just a matter of I need all the help I can get because I'm a lost cause, and that's just how it is. So let's go with it. I started programming at 8. I had an infatuable fascination with computers. I've always loved what computers have been able to do from a young age. It's just crazy how much performance they have in terms of sheer data manipulation. At one point, I was begging my mother at 8 years old to take me to Target to buy a C++ book, and it was called You Can Program in C++. Turns out 8-year-old Austin, that's my real name, could not program in C++. It was quite a jump to go into. So my first official language was Microsoft Batch, batchfiles.bat. And so I started making like text adventure games, a bunch of other various scripts. After a while, I sort of graduated once I understood like control flow and some other stuff, and I led into at that time Minecraft was just coming out, Minecraft Classic and then Minecraft Survival, like the Java edition in 2010. I was 10 years old at that point. My age follows the year. And at that point, that had just come out, and I was infatuated as a 10-year-old playing Minecraft, all that sort of stuff. And the only thing I thought was, I want to be able to create content. I want to be able to modify this and like see what that looks like. And so my first real language was indeed Java, and that's where the bulk of my learning happened. In creating mods for Minecraft, and then also creating like servers for Minecraft and Bucket plugins and some other stuff. And so if people will tell you video games are rotting your brain, just tell them not if you're creating the video games. That's all you gotta do. So because of that, after high school and my program career, I went to college for a computer science degree, and I dropped out within the first week. I got the first bill I took my tuition and I put it on a monthly or a weekly plan of payment. And I quickly realized, both after talking to some senior students and some other things, that like I was going to be a lot of money in debt, and I was scared. I didn't know how I was going to pay it off. I didn't know what that was going to mean. And I just didn't necessarily feel like I was getting the value that I needed for the amount of debt I was going to be acquiring. And I feel like that's a hard decision for a lot of, at the time, 18-year-olds to, work with, understand the full consequences and work forward. So I am officially a college dropout, and I'm here to tell you it does not 100% matter if you have a college degree. I began my career as an electrical contractor. I am ICCC certified, the International Construction Consortium. I have a commercial electrician's license in South Carolina and other states. I no longer live in South Carolina, but electronics was my first go-to. I did all that, but after a little while, I was a subcontractor, and then I kind of moved out to Denver, Colorado, where I'm at now. And I migrated back to computer work in 2021. And I migrated to customer service. I originally was through a PDF engine in Belgium, and they were a PDF engine for external companies to generate PDFs with. And I was an integration specialist, so more of a technical support role because I was technically minded. Now, I did not have a degree or anything, so I did not join in directly as like a crazy developer or nothing. It was purely the fact that I was good at programming and also pretty decent at talking with people. So I was in customer service at 2021, helping our B2B clients integrate our product and what that meant in building POCs for them and helping their developers with support. I quickly realized that I enjoyed the software part of it way too much. I love data structures. I love algorithms. I love how things work. I love creating things. So I migrated into software engineering eventually in 2022, only a year later at that company. And then about a year later, the current company I'm working at, Jam Plus, picked me up as their print specialist, lead developer, that sort of stuff. And so I was doing a lot of PDF, a lot of print stuff, and now I kind of span the entire gap of front end, back end, devs, ops, that entire thing. That's me. That's me with my crystals. Those are the two crystals I keep at my desk, and so always got to have them. So let's go ahead, because I'm a programmer and everybody loves programmer hot takes. Let's get the hot takes out of the way. I love these. All programming languages suck. I want to get this out of the way. So why do all programming languages suck? And it's because that they're just that. They're a language. Just as human languages are honestly an awful attempt to convey human emotions. And each language has their own way that they decide to do this. Like if you know Russian, they have 6 different pronoun cases. If you know English, they kind of take a more simple approach. Programming languages are similar. At the end of the day, all we're attempting to do is convey languages in this very large... we're attempting to convey emotions. And for computers specifically, it boils down to ones and zeros. That's it. Computers only know 1 and 0. That I hate to break it to you, that's all your processor knows. And each language has different ideals and methods that they do this. There is no magical solution. If there was, there would never be the question of which language is the best. That's all I have to say about that. If we had a magical answer, this wouldn't be a controversial hot take. So why is that? Well, why is that is very simple. Humans suck at communication, and we have a lot of stuff to back this up. If you haven't done enough psychedelics like I have, basically, emotions happen in real time. We think in emotions, and then we attempt to break those down into communicatable language. We hope that we can take the way we feel, why we feel this way, what's going on, how we want to get to X, Y, Z, and because of that, and then we attempt to break these down and force them into a box known as language, and then speak that to another human, and then we really hope and pray that they can unpack all of these words, all of this tone, all of this connotation, and then unpack it to the emotions that we're attempting to convey. And this process alone has tons of pitfalls. And these pitfalls are what we tend to call miscommunication. And as I think even Leith mentioned earlier, communication and speaking is hard. It takes time, it takes talent, and trying to convey your words as expressively as possible and as concise as possible and hope that other people get it is truly an art form. It really is. And in programming, we even have something called Conway's Law. And this was created in the 60s by, I think his name is Melvin Conway. Let's double check. Let's fully check. Melvin Conway in 1967. I just confirmed. And it was basically from an original paper called Design by Committee. And it was a proof of concept that describes that the systems that you design are fully limited by the communication structures that are limited or are created and imposed within your organization. It's that organizations are constrained to produce copies of their own communication structure, and that's just kind of how it works. Where the API barriers lie within your own organization end up being where the APIs lie within your programmatic systems. So it's just kind of how it works. I don't make the rules, but it is true. So next hot take. Remember how I said languages are interchangeable and all suck? Yes. So that means you should learn the one that's most worthwhile for you. If you want to be in data analytics, you should probably learn Python or R. I mean, those are the best data analytics languages to know. If you're embedded systems and that's what your passion's about, then probably learn C or C++. That tends to be where they, go. If you're genuinely without a loss, like if you are saying, I want to be in software, I don't know where to start, I know that's where I want to be. Well, my recommendation is probably going to be JavaScript, because every company on the face of this planet has a front end. Web apps are the future. That's where everything's going. So JavaScript is probably going to be the most easiest barrier of entry way to get into a job as a developer or full stack, and you can go from there. Next hot take, let's keep going. Oh, I went up. Next hot take, tooling comes over time. As even earlier we talked a couple times, a lot of people get very buried early on into tooling and thinking that tooling makes them a better engineer. And I'll just say this by example. I did not learn Vim on my first day programming. I did not learn Vim for my first 2 years professionally developing. I learned programming, and that's what pays, is learning programming. Tooling does not make the engineer. Next hot take, tooling makes the senior engineer. If you ask a junior engineer a problem and how they would solve that, they're going to give you a very good way of theory and approach and problem solvability. However, the senior engineer, when you ask Scott, when you ask Sending how you would solve this problem, what they're going to do is tell you exactly what they would use, why they would use that, what they wouldn't use, and why they wouldn't use that, and how they've shot themselves over, the many years that they've been doing it. And that's just only comes from experience. And if you're looking to get in this industry, you shouldn't be shooting for experience. You should be shooting to get into this industry. And ultimately, the best way to shoot yourself, or the best way to know to not shoot yourself in the foot, is to have shot yourself in the foot so many times you go, ow, that hurts, I don't want to do that again. And that's just kind of how senior engineers are built. So don't worry about tooling. Worry about being practical. Worry about deriving value, being a good engineer in the actual core fundamentals of engineering, because those are what's going to take you very far. And the tooling will come over time. I learned Vim and all my fancy IDE features over time because those helped me and proved to be beneficial. But did those make me a good engineer? No. They just made me a better engineer. And that's what I think is why that's a hot take, I don't know. Math is the best language we have for describing systems, and that is true. I was talking yesterday about how there's been a couple times throughout my career where, unfortunately, I stumble across an entire system of thousands of lines of code. And as much as I respect the hustle and respect the dedication, it's thousands of lines of code that didn't need to be. It's truly systems that were created domain specific, as in they were created to solve a very specific problem within the context that they're being applied. So for me, that's printing. So it's like, well, this is attempting to determine pricing on a folder versus an envelope and very specific stuff. And you can see that within the source code, because they're even in the source code, variable names are like printing and add, that sort of stuff. And when I take a step back, I really try and view it as an abstract thing, and I'm like, hey, we're doing a set intersection of a combinatoric set here, and that is unfortunate, because it's like most of this stuff can be built into your systems for free. And math is the way that we know how to reason about our world around us. Math has done their best ability to sort of reason and make functions and make understandings of how the world around us actually works. And so it does pay off to learn that abstract language of math, because then you can sort of begin to realize where all the overlaps are and where you can kind of apply and understand and say, hey, we're not talking about this very specific, domain model complexity thing. We're actually just talking about this math abstract idea that thankfully has been solved long ago. And also thankfully we have tons of libraries that are formally provable and are very well tested. And we don't want to own all of this stuff. We want to use formally proved, very reliable libraries that can help us out. That's what gives us fast business value, and that's what gives us the ability to move quick and also just kind of be able to rely solidly in our application. So building systems is easy, and this is one that I think a lot of people get tripped up on. A lot of people think that building systems is what makes an engineer, and I kid you not, it is, in my opinion, the furthest thing from it. A lot of people can build systems. The hard part is building a system that can be maintained for 10 years. I see it through and through again. People build systems, they get the job done, business requirements change, the system can't adapt, you inherit tons of technical debt, and here we are 3 years later rebuilding the same system over and over again. And it's just the same story retold. The hard part about engineering is building a system that's reliable, that can scale, that understands that business requirements change, and that people can upkeep for 10 years, and especially other engineers. And that is, as I say, any engineer can build an API. It does take a talented engineer that can build an API that can scale up, can scale down, and can be maintained for 10 years without being rebuilt. And my last hot take is do what you love. It's actually very painful to not. I love what I do. I love programming. I love software. I love problem solving, and I love engineering. And that's why I'm doing this talk, is because I love it and it comes natural to me. And if it didn't come natural to me, it would be very painful to give this talk. I'd have to go out of my way for hours to sort of try and design everything, think of what I want to say, think of how to say it, and that sort of stuff. It is true. If you find something that you do genuinely care about, even if you don't care about the programming aspect of it, find a sector that you care about. Do you care about space and technology? Do you care about, defense? Do you care about e-commerce and selling things? Like, find something that you care about, because it genuinely will make the process easier and make it more fun, and you'll sort of realize throughout the long term that it's much more natural. You don't have to try. And I think a lot of I'm not necessarily in a role where I interview a lot, but I have been interviewed a lot, and I think it becomes very evident when you care about what you do and what's going on, and you have the ability to reason about that and the experience, and it becomes very evident to the interviewer, like, oh, this person does care. They do know what they're talking about, and like they've shot themselves in their foot enough that they know what's going on. So finding a system that you love in a career that you love really will pay off tenfold, because everything else sort of works itself into place. And that's an amazing thing to realize. All right, so now to the core of my actual talk, which is contract development. And so let's start with, what is a contract? Like, definitionally speaking, a contract is a written or spoken agreement. And so why have a written or spoken agreement about your system? And that is a very important concept that I think really separates seniors from juniors in terms of stuff. One is that you begin to start having design abstracted from implementation. Implementation is sort of only a means to an end. It's only a way to get from point A to point B. It's far more important to describe what point A and point B is, as Sending Grounds within his last presentation described. At the end of the day, shareholder value only cares about what A and B is and how we get there. Now, actually implementing that is up for the engineers, and it's a matter of how fast, what it looks like, that sort of stuff. But really, it's amazing that we can take a step back and figure out what point A is, what point B is, and what our requirements, our issues, and sort of stuff is from that. Now, contracts have this beauty where they can scale for multiple actors. Now, an actor in like the literal definition is anybody that acts upon something, but in this case, it's basically anybody that has to deal with the contract. Anybody that's dealing with the data, dealing with the system, and how the system is described to work contractually is an actor on that system. And the beauty of a contract is that it's actor agnostic. Whether you're dealing with a front end, a back end, or anything, those are all simply just actors. They're replaceable. They're going to change over time. And as much as we love to care about them, we have to think about the bigger system as a whole. And so thinking and refining the bigger system pays off tenfold instead of thinking about the actor itself. And what that also means is scale for multiple languages, because actors, like I said, deal across a variety. You're going to have a front end. In the front end, unfortunately, you only get to think in one thing, which is web. You get to think in HTML, CSS, and JavaScript. Those are your only three options. And so what if you don't want to build your whole application in that? That's not necessarily a normal thing to build your whole application in HTML, CSS, and JavaScript. Well, now you need a backend, and your backend's going to be in a different language. And they're all going to have to think and reason and agree with this contract. So that's why it's amazing to have a contract that isn't tied to the actual implementation of the system. And then the last thing is refactoring without behavior loss. As we all know, in industry, things change. Shareholders change value. People change value. Business requirements change. They get added. They get removed. And so what you end up needing is a way to reason about these changes across multiple systems all at once. And if you don't have a way to reason about these, then you rely on pure raw human communication of telling some multiple team leads like, hey, we're doing this. Hey, we're doing this to the front end. Hey, and you now have to try and normalize and standardize across multiple teams how the system is changing. And chances are, I've seen it through and through, each team's going to come out with a different interpretation, and then you're going to spend many weeks trying to reconcile those interpretations into an actual like an implementation. So contracts help define that actual middle ground between what the system is, what it's doing, and sometimes it says why, sometimes it doesn't, but a good contract will say why. But it really tells you what you need to do, why, and how you need to do it, like what you need to output, what you need to take in, that sort of stuff. And that is what's beauty, is that it spans multiple systems. Here's a little not a pie chart, like a bar graph I created. I think a junior dev spends, a large percent, 90% of their time programming and a very small percent of their time designing. And then as you get to that later scale of like senior dev, you start spending a lot more time designing and basically eliminating how much programming you have to do. Programming is purely implementation specific. It changes, it's disposable. As much as we love to do it as engineers, we should really be trying to figure out how much domain complexity we have to take on, how much we have to eat, and how much we can simplify. And those are the amazing things about that, is as you go, you sort to realize like, I'm better off spending time figuring out how to simplify the problem instead of how do I implement the whole problem. And a good talk about this, and another reason I love Clojure, it'll be in my references at the end of it, is they call it hammock-driven design. And it's by Rich Hickey, the creator of Clojure. It'll be in my references, like I said, at the end of this presentation. And it's basically the philosophy, as you've seen, test-driven design or TDD or some other things. Rich Hickey basically talks about hammock-driven design, which is like the best thing you can do to design is sit in a hammock for hours and think about your design. Because there's a couple things that are true about test. If you think about every bug that you found in production, what happened? They passed the type checker. They passed the unit tests. They passed the UX test, like the actual test. Every bug in production passed all of those things. And my favorite analogy about unit-driven testing is what human takes their car onto the highway and starts bashing against the barriers to get them where they want to go? The answer is none, but that's what tests do. The tests just define the barriers of the highway and hope you're bashing into the left and right barrier of the highway, and it's teaching your program where to go. And it's not really no human does this. No human gets on the highway expecting the barriers to keep them on the highway. No, we follow the lanes, we know where we want to go, and we try our best to define what that is. And that's where hammock-driven development can really help you figure out your design and, narrow your focus and get that good. So what is our first contract in programming and in computer science as engineers? Well, the original one was types, and that ended up happening in the early 1900s. We had this thing called type theory, and it was originally from math. We had type theory, which was an extension of formal logic, and like set theory, which was these mathematicians came up with these very fancy ways to prove everything. However, they sort of got stumped about provability and certain unsolvable paradoxes, which in logical theory, like there's a lot of what we call logical paradoxes. So they created type theory, which is like, hey, if it kind of looks this way and does this way, then like we can sort of like compute across it and produce new types and that sort of stuff. And so type theory was like a very specialized computing form of math that proved to be very positive and usable in computer science. Now, what that looked like in actuality was basically a promise between you and the compiler and the computer. At the end of the day, computers and processors only understand ones and zeros. That's all they understand. So if you see at my little chart here, my little image, what I have here is the binary representation of a IEEE 754 float 64. Now, for all of us that are not massive programming nerds, that means a modern decimal number. That is what that means. That is what that looks like to the computer. That 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, that sort of stuff. That's all that is stored in your computer is those zeros and ones. So if it's only zeros and ones, and that has to represent strings, characters, floats, integers, every single thing that makes up Discord, everything, how do we begin to reason about that? Like, how do we understand what 0 means what and what 1 means what and how does that scale? Like, how can we ever even begin to comprehend what those zeros and ones mean? Well, the answer is contracts. We have to have a contract within the memory of our own computer to say, hey, if I have an array of 0 and 1s and I'm saying that contractually this is a floating point 64-bit width integer, that this is how it's laid out. And that's what that means. That's what IEEE 754 defines. If you want to get very specific, you have like the mantissa and the exponent and like that sort of stuff. But what that means is if I give a compiler that array of ones and zeros and the specification of floating point 64-bit width numbers, then I know that that unit of memory means 101.24. And that's what it means. And that's because we have a contract between us and the computer to say that contractually we have these lenses. And that's basically how I view it is you have raw memory in your computer, which is this big array of ones and zeros. That's all your computer knows. But the compiler, the computer program, whatever, has this ability to change glasses. And these glasses are type glasses. And it allows it so when you put on this pair of glasses, these ones and zeros look a very specific way to you. So I have my float 64 glasses. So when I look at this memory, it looks like a float 64, like a decimal number. Well, when I have these string glasses, when I go grab my string glasses and I put them on, well, suddenly these ones and zeros look like a sequence of characters that make up a sentence. And so forth. So we have this way, this contract with our computers to say like, hey, this memory is laid out in a certain way, and this is how we're going to view it, and that's what helps us sort of reason. Now we have static and dynamic typing, and y'all would know this between static and dynamic languages if you are in computer science. So we have like static languages like C, Java, C++, Rust. And that's where we're sort of like dealing with types in the static compile time and like understanding what these binary representations means at when we're writing the code. And then we also have dynamic, which is our more modern interpreted languages like Python, like JavaScript. It does not mean that the types go away. It just means we don't care about the types until we actually have them at runtime. That is why you can get untyped errors in JavaScript in the web browser at runtime, is because like it was expecting the bits to be this one way and the bits were not this one way, and it caused a massive issue. And so you sort of have benefits or not, and the beauty of, and I just want to add this as an interjection for a nerd rant, static versus dynamic typing, these conversations and these arguments over which one's better, which one's been around longer, they existed all the way to the math days. The beauty is that even, and I'll read this, back in 1920s when Alonzo Church created lambda calculus, he created two variants. He created simply typed calculus, or simply typed lambda calculus, and dynamic. And the difference is basically this. In typed calculus, functions can only be applied if they match the type of the data that the function accepts. And in dynamic, it's much more of a weaker style of like duck. If it works, if it quacks and talks like a duck, it'll work. And basically the primary thing, the difference is that in formal typed systems, they're provable. You can, at static time, not in the runtime, not in the wild, but before you even deploy your application, you can sit back and say, mathematically, this system can handle anything it throws at it. Now, the downside of that is that you have to define every single thing that can come to that system, and that is hard. Defining every single possible type of input, every single what that looks like, how you handle that, what's going on, is a hard process. It takes a lot more development time. It takes a lot more to reason about. It's a slower cycle. And then in dynamic, you can start to be like, oh, as long as it matches this sort of contract, it'll just work. And like you can start generating contracts. You can start generating more types. You can start doing this much more flexible style of programming. And that's sort of basically the main difference. If anybody ever wants to argue with you about statically typed programming versus dynamic, the difference is flexibility versus provability. Static systems can prove themselves a lot easier but are far less flexible, and dynamic systems are far more flexible, but there's a lot of times you can't prove that they're going to do exactly what you say they're going to do, and that's kind of the big challenge. Is like, do you want to be more flexible or do you want to be more sound and reliable? And that's the biggest thing, and that's pretty much what it's always been. And my basic only point of this is that it has existed in math since the 1920s. This is not a new problem, and it's going to continue to exist. So let's talk about the history of contract implementations in software systems. Now, I'm going to go ahead and try not to bore you. I'm a huge nerd, but I am going to give you some background of like what we did as computer scientists, how we got to where we are, and what we learned from each of those things. So the first one is static type systems. That's what I described originally. In C, originally in like the 50s, we basically described how we need to describe the bits over the memory to figure out what they are and what they mean. So that was our first contract with computers. Well, then by the 1970s and 80s, we wanted to start making more reliable, applications. So we started thinking like, what if we could make the contract stronger? Like, what if we could like really promise with the computer what things are going to be? Because we ran into a couple issues, and some of those are like, let's start with like Ada and Modula 2. Those are two examples of languages that came out in the late 70s, early 80s that sort of improved this ability of stricter types. And what does that mean? Well, that means like Ada introduced the concept of range constraint types. Well, what does that mean? That means that like you can tell in the language of Ada, which was a Department of Defense language, you can say, hey, this is not just a number, but this is a number between 0 and 360. And that's all this number can be. And that proved very useful for like things like degrees, like a rotational degree is really, while it is an integer, it's only an integer between 0 and 360. And if you give me 361, that's not a valid degree. I don't want that. So these languages started giving you ways to range constraint your types and to start defining more specific contracts of like, how can this data really be? And in that, we got subcontracts or subtypes. And that includes types that share the same representational binary data, as in under the hood, they're just a number. However, they're not compatible numbers. And my example would be like speed and distance. If you're working with a formula in like, if you're a radar system, and you're taking a function of how far something is away from you, and you need to know its speed and you need to know its distance, you do not want to get those mixed up. If you get those mixed up, you are going to be very far off in your calculations. However, under the hood of the computer, speed is a number and distance is a number. So if you just say, I take a number, you will not be as accurate as saying, I need a speed, and this is what a speed is, and I need a distance, and this is what a distance is. Even if they're both numbers under the hood in memory, you now have this ability to really strictly say they're different things, and I need to reason about them differently. And that's an amazing power that these languages had, and that's why we started inventing these very stronger types. Another thing was I'll only brief on this mission, was like explicit conversions. Sometimes we need to transfer data from what they are. We need to transfer data from a speed to a distance, speed over time, that sort of stuff. But in C, in the in the original programming languages, we didn't have a way to reason about, hey, this address in memory is this concept of a number that can be interpreted these ways. And it sort of allowed you to interpret it any way you want. But now with these stronger languages, we had to say, hey, these can only be interpreted in these specific ways. And that really helped give our computers rules that they could enforce to help keep our system safe. Because, like I said, when you're programming a nuclear warhead, you do not want to get speed and distance mixed up. That is the difference between nuking North Korea and Europe. And those are not decisions you want to take lightly. So next, after that, these stronger types, we sort of realized that systems do not exist in one facet only. We really realized that systems kind of span across this whole thing of different computers, different languages, different actors, things going on with it. So we fast forward to like the 1990s, once we get into Corba. Corba is Common Object Request Broker Architecture. And it was this basic idea of we have multiple systems that want to talk about the same data, and how can they do this in a distributed fashion? And what that turned out to be was you define your types and your operations in this like neutral interface called like interface definition language, it stands for IDL. And you would basically write out what this neutral contract was between languages about data. And then each language would generate its own specific typing, its own specific, compiler memory layout of what these abstract ideas mean. And so what that was like, now you can talk between multiple different systems with multiple different memory layouts, with multiple different ideas about the same, general concept. And that was an amazingly powerful thing, is that you could now reason about these abstract ideas instead of referring to specifics. However, in actuality, what this ended up being in the early 90s, we didn't really know what this looked like and how it worked. It became very complex. It was fragile across networks. Anytime state was used within objects, it just didn't replicate well. It didn't go really well. Now, outside of the scope of this talk, if you are interested in like, how can we talk about distributed objects across networks, and you want to go learn for yourself, the answer that we have nowadays is called the actor model, and it's what's used in the late 80s. Ericsson, the telephone company, created Erlang in the OTP, which stands for Open Telecom Platform, and they created the actor model, which was inherently stateless, in a way to talk about objects across a network distributedly without state and sort of replicate themselves. So if you are interested in like, how can we talk across multiple systems of objects in that nature, then I would recommend you look into like the modern day Erlang, Elixir, and the OTP. But so after that, we got Java interfaces. And Java interfaces were basically, they said, instead of going stronger types, how about we go wider? What if a type wasn't specific to its memory layout? What if a type was only specific to, could it jump like a dog? Could it bark like a dog? Could it, what if we just had to describe how things work instead of like actual specifics of things? And that was an amazing thing. Java came out in the late 90s swinging with these sort of ideas of, let's not think about any implementations, let's only think about, can it do this? And I don't care what it is, I only care about if it can do these things. And so that's really where we got into this abstract ideal of not thinking about how it's done, but what is done, and defining what is done instead of defining how it's done. And so that was amazing. Java did a really good job at defining interfaces, if y'all know OOP programmers. These are Java interfaces. These are C# interfaces. This is the modern OOP interface term of saying, hey, if you can abide by this general contract, then I don't care what you are, I will work with you. And that was amazing, because no longer did you have to build systems to take one specific thing. You just had to build systems to define what they needed to work. And then as long as somebody else could say, I can do that, then they would work with your system. And that was super powerful. However, we realized that only worked within Java, or only within the language that it was. So we started trying to figure out, in these distributed systems, how do we define these abstract ideas that can work across systems? Well, the next thing was structured data and contracts for that data, and that's how we got to SOAP and WSDL. SOAP stands for Simple Object Access Protocol, and WSDL stands for Web Service is Description Language. And that was basically sitting back and saying, let's not pretend that we're one big simple system all on one computer. Let's actually understand that we are multiple systems across multiple computers, and we're all trying to understand the same thing. And so that's what it was defining what that thing was. And that's where we got to our lovely first data format, which was like really big, and that was XML. And XML was a very powerful file format to attempt to describe what data was, to send data, to describe systems and how they work. And so first we had like XML schema. And XML schema was a way to say, hey, this data looks like this. It does these specific things. When you send this data, it needs to follow these rules. And that XML schema would follow the data, or the data would reference its parent schema. And you would be able to validate and reference that schema for those objects and that data and say, like, are you valid? Are you aligning with what you say you are? And if you aren't, then how do we deal with you? That sort of stuff. And that was a powerful concept, because up until then, we basically kind of took data for what it was and hoped it was the best. And if it wasn't that, then we would blow up hard. But now we sort of had a way to reason about data and say, like, I'm supposed to be this, I'm supposed to do this, and this is how I look. And if I'm not like that, then like, here's some ways that you can attempt to recover me. But we also did that with our systems. Like, we started describing systems in XML, and that's where we get into the WSDL, Web Services Description Language. And that means, like, how do we describe these systems that take data in a way that we can start abstractly from implementation talking about, like, oh, this creates a user, as Sending Grounds talked about, right? Oh, this creates a user. Oh, this deletes a user. Oh, this will get all the addresses associated with the user, right? We started finding ways that we could describe these fundamental business operations that wasn't code. Because code, as I said earlier, languages are interchangeable. They're agnostic. They kind of all suck. So we really wanted a way to describe behavior much more than how it did it. And that was what WSDL gave us, was a way to start talking about behavior and not how things worked. Now, the downside of these, and why we still don't really use SOAP and WSDL, is that they were extremely verbose and extremely complicated. Unfortunately, you sort of have this ideal where XML can go with both attributes of the node and children of the node, and it starts making double trees where you can go out, and it's very hard to reason about. It's very hard to prove, but it's also incredibly hard to build tooling around, to build systems around, and to like build standards around. When things become so generic that they're hard to reason about, they become too generic, and you can't build reliable systems around them, because it's like you have to think about 20 million use cases, and for an engineer, that's just not possible. Our brains are not big enough. We can't comprehend enough to understand 20 million different ways to use the system. We really have to simplify down to like very specific contracts of like, here's how you use the system, and that's what this means. So unfortunately, SOAP and WSDL didn't last forever because it was a little bit too complex. So what does that mean? Where do we go to after that? Well, in the early 2000s, we were kind of tired of this over-engineered, very complex stuff, so we created REST. And REST just stands for Representational State Transfer. And it gave a very simplified idea of building APIs. And if y'all don't know, API just stands for Application Protocol Interface. It's a way of dealing with systems via code, how machines talk to machines. And this was far simpler. It was like a way of taking a step back and saying, like, hey, what if we didn't need to understand all the specifics and all the different, like, what if we just very simply described systems and what they do, but like in a very abstract manner? We don't really care much about anything. And so REST came to be very popular. And so REST became very popular in the early 2000s, and we started using JSON, which is JavaScript object notation, in the early 2000s instead of XML, because JSON was also a much more simpler way of talking about data. It didn't have attributes, it didn't have anything. It was just a way of very abstractly describing data. Is it a hash map? Is it an array? Is it a number? Is it a string? How can we very simply send data in the easiest use case possible? It was smaller because for anybody technical here, it's way smaller than XML because it doesn't have closing tags. There's no tags in JSON. It's just a tree structure. You write it as a tree and you interpret it as a tree. And so it's faster over the wire because you no longer have tags. You no longer have all of these sort of ceremony that XML had. So it became very appealing because not only was it faster, it could express just as much, and it was easier to work with and far less for people building tooling around it to deal with, like parsing. You no longer had to deal with attributes that could be nested. You no longer had to, you just had a tree structure that you had to parse. And so because of that, it became very popular. And so by the 2010s, I would say, REST in JSON ended up becoming like where we're at now. We are very much a REST in JSON, very specific industry as a whole. Now we've built tooling on top of that, and I'll get to that closer. Like we've built GraphQL, we've built other stuff on top of that, but we're pretty much at the end of the day still a lot of JSON, a lot of REST. So I just want to summarize that if anything, if you take anything out of this or anything out of this slide, really we kind of learned something from all of these things. And most importantly, we really go in this big circle. And that big circle is that we start with strong contracts for safety. We want our systems to be safe. And then we loosen them for flexibility and simplicity because, like, if you overly specify the system, then it becomes, even as Scott said the other day, when protocol, like practice ends up overtaking protocol. If you specify something super specific and then you go and say, oh, we don't actually do that, it's too much, we really just do this, and like this is all you need to know, then what's going to end up happening is that your practice is going to become your procedure, right? And so we realize like it's actually better to just sort of define the procedure in an easier way to comprehend so more people follow it. So we loosen them and we give them flexibility and simplicity. Well, then things get messy because people take it too far. They loosen it too much. Systems get dirty. There's no longer way. And then we add just enough contract in again to make them reliable again. And then we sort of like repeat this loop. And we've done this for 50 years over software, It just sort of repeats itself over and over again. And like to tie it back, those type glasses, those little glasses that you put on to look at the data and understand it a certain way, they never went away. They just kind of kept changing shape. And we just kind of kept, evolving with them. And that's kind of an interesting thing. But nowadays we have these contracts that are built upon, and that's kind of what I'm here to share is like these modern what does it look like now? And how do we reason about this data now? And how do we move fast with that? And so that's looking like open API specification and JSON schema. And that's kind of where I'm going to like run into that. So what is JSON schema? Since we've kind of defined that JSON is kind of how we talk about data over the wire now in like an easy way that's text encoding agnostic and other stuff. Well, JSON schema is basically an abstract way to define data throughout multiple systems. You're kind of describing the shape of the data, and then you're building that contract. That JSON schema is that contract with that data. You're saying this data has to do this, this, and this in order to be valid data. And that's kind of what we love about it, is that it's kind of agnostic, because one thing that is very true is that type systems are language specific. And if you build your application in the type system of your language, unfortunately, you're building your system to be tied to that one language. And I run into this a lot. And this is what's really hard. I know a lot of people that love Java interfaces, but if you start describing our entire system in Java interfaces, that does nothing for the front end. That helps nobody in the front end. That helps nobody that's building Lambdas and Go on AWS. That does not allow us to start describing data as data. It really forces us to describe data as how it looks in that one specific programming language. So what JSON schema attempted to do was say, well, how do we describe data as itself? How do we start making these portable type systems that can kind of run in any language, that can validate any data? And that's what JSON schema really is it's a way to start describing what data looks like as data. And then you can start getting these benefits. In certain modern things like Zod on the TypeScript front end things, you can start doing runtime validation plus transformation, which yesterday we talked about, I think it was ETL or something, where it's data transformation during Timotheus's presentation. The one thing's for sure, users are going to input shit data. It's just going to happen. We cannot get around that problem. At the end of the day, we're paid to take data in and give data out. And we're not promised that data coming in is going to be perfect. It never is. It never will be. But what we should do is not allow that to poison our entire system. Because if you have to if you think about this, if you have to sit in your entire system and expect all the data to be potentially corrupt and potentially poisonous, then you're going to have suddenly a very hard system to reason about. If every function has to sit there and go, well, maybe the user's not there. Well, maybe the da-da-da. Well, now every function has to inherit all of this complexity of this crazy amount of user data. So what we like to do in a data-oriented system is we call it the walls. We love to build these Roman fortress walls. I want everything in my system to reason about data in the way that it knows how to reason about data. And I want every user input, every machine input, every API to come through a front gate. I want guards standing there at the front gate going who are you? What do you look like? And if you aren't in the right way, then they're gonna hit you with their polearm. They're gonna stab you until you become the right way. But that's what the great thing about these runtime validation and transformation is that you can now have these guards on the outside of your system sitting there protecting all the functions within your system, saying what do you look like? Who are you? And if they aren't able to work with your system, well, you can start telling these guards how to help these people deal with your system. So sometimes you'll get a UUID. I'm sorry, a UUID is a bad one. Sometimes you'll get a Boolean as a string instead of a Boolean. Now, JSON accepts true, false, but sometimes a system or a user is going to send those true, false in quotes. And it's just going to happen. Systems aren't perfect. I don't make the rules. But what shouldn't happen is my entire system blows up because somebody decided to put their Boolean in quotes. And I'll stand by that's on me. I want to be resilient. I want to be reliable. So what I'm going to do is I'm going to describe guards that can sit at my front gate and say, oh, I need you to be a Boolean. What are you? Are you a string? Well, let me look at my book of how do I deal with strings in this data format and make them Booleans. And so that's what they can do. And you can start describing these JSON schemas to handle these things with regex patterns, with sort of stuff. And you can define what these guards look like so that they can take your dirty user data, your dirty machine data, and they can transform it into data that the rest of your systems can safely not have to worry about. Because you do not want every function in your system to have to deal with dirty data. It's just too much. You're gonna run into pitfalls. You're gonna run into situations where you didn't think this is quite the data you thought it was. And it's just kind of nasty. And so it's better to just have guards at the front gate and to tell those guards how to let people in and what to do if they aren't allowed in, to let them in. And it works really well. And these sort of schemas will give us that ability. So next we have version and change management. And that is, one thing's for sure, We don't know what we want to build, whether it's us as software engineers or whether it's us as business, professionals, whether it's us as the board or whatever. Things are going to change. Business requirements are going to change. And if you build a system that can't change, unfortunately, you've kind of failed. And that's a really tough reality that I think I've learned the hard way, where it's like, I have this great idea of how this system's going to work. And it's like, oh my gosh. And I implement the whole thing. And then it's like, no, well, we need to add this. And it's like, well, if I knew that, I wouldn't have built it this way. And it's like, well, we need to add this. And now I'm left with tons of tech debt, tons of refactoring. And so it's really nice to be able to describe up front and to know up front and to build a system up front that knows things are going to change. Because one thing's for sure, things are going to change. And that's just what you should be building as your system, because like, you're either going to fail or you're going to change. And that's an amazing thing to sort of realize and start implementing, and realize once you sort of implement the abstract idea that this isn't permanent, it's a single version in a subset of potential versions that's going to keep growing, you can start building systems that take versions to go to other versions, and you can build schemas that keep just progressively updating. And all of a sudden, this kind of problem goes away. And it's amazing how once you accept the problem and feel the problem and put the problem into your contracts, the problem really does sort of go away. And the last thing about JSON schema is that it's written in JSON. It's sort of like a homoiconic, which if you don't know what the word homoiconic means, it means that data is written in the language it describes. Lisp is the biggest example, but it basically means that we describe JSON data in JSON. And that has a big superpower. When you can describe things in their own terms, you start inheriting the own complexities of the problem domain. And that gives you a big superpower, because you start speaking the language. You inherently speak the language that it speaks. And that is a big one step ahead in that sort of stuff. So JSON schema does a very good role there. So I'm going to go ahead and jump into an example system. So I just want to give us an example system so we can kind of see how this actually looks in actuality. So let's say that in our example system, I don't know why my animations aren't working. Oh, wait, no, what? I don't know how my animations aren't working, but we're going to go back. So let's say in our example system, we want to track engineers across platforms. And what platforms mean is, like, we have in Prolog, we have let's say we have Het streaming, we have me streaming, we have Sending Ground streaming, and we all want people to like be a part of this Prolog this ecosystem. And we also have the Discord, right? Like, we have all these different platforms that have different ways of thinking about users, thinking about data. Twitch plus Discord. And we want to start with certificate tracking. We want to allow engineers to track their certificates no matter what they're in. Are you in Discord? Don't care. Are you in Twitch? Don't care. Are you in, we don't care. And two things we know for sure, right? We know that more platforms are going to come. Discord won't be around forever. Twitch won't be around forever. So if we build our systems to be specific to Twitch and Discord, we are right then and there taking our Colt 1911 and bringing it out, cocking it, and shooting ourselves in the foot. Because the day that Discord goes dead, it's like, why did our system break? It's like, well, because you built it around Discord. And that's a bad idea, because other systems will move on. And that's not a good way, is to build around other systems. You're an engineer. We're engineers. We build beautiful systems. And if the base of our system is reliant on somebody else, well, suddenly we have a very large issue that we have to solve. The next thing is that we know more features are to come. What happens when certificates change? What happens when they want to start tracking more things other than certificates? An engineer needs to be able to grow. We don't want to make an engineer specific just to certificates. So what that really means is we don't actually know what we want. We have an idea of what we want right now, and it needs to be able to change in the future, and we need to be able to adapt to that. So let's actually see what that looks like in JSON schema. So in JSON schema, let's start with the first thing we have is like a certificate. And so I'm not going to go directly into the specifics of JSON schema. I have included it in our resources, but it's a way of describing JSON. And right now we're describing an object in JSON, which is a map and a mapping of properties to values. If you don't know what a map is, I can't really help you. It's a fundamental data structure to computer science, but the best I can say is they're Python dictionaries, they're JavaScript objects, they're Java hash maps. It's basically this idea that you have a key and a value. And so what we're saying here is that a certificate has a description and the associative arrays in Bash and associative arrays in PHP and Lua. You have all, like, they exist in pretty much any language you can want, and they're a beautiful thing. They're one of the most fundamental data structures. And so what we're saying here in this schema is we're saying we have a certificate. Now, what is a certificate? Let's give it a description. Let's say a certificate is an abstract certificate that engineers can earn. Which is true, right? When we're as engineers and we go work for a certificate, what are we getting? We're getting this idea of like, this is something that says they know this and it has a title and stuff. So let's describe what it is. Well, I'm saying it's a type of object because we're in JSON. But what that means, it's a map. It's a mapping of, keys to values. And so let's describe what these key and values are, in an abstract way that isn't specific to Java. It isn't specific to JavaScript. It isn't specific to, any of these systems. And so we're saying that the properties of a certificate is that it has a title. Well, what's a title? Well, we can literally say it's the name of a certificate. An example being AWS Certified Solutions Architect. Well, how does that look in data? Well, that looks like a string. Our title's a string. Okay, well, what's next? An issuer. Okay, well, what's an issuer? Let's give it a description. It's an organization that issued the certificate. Okay, that makes sense. Somebody has to issue the certificate, so let's write down that, a certificate needs an issuer. And how does that look in data? Well, it looks like a string. And an issue date. Well, what is that? It's when the certificate was issued to the individual. I actually forgot one thing on the slide. I added a UUID. You'll see it later on. I should have updated this. A UUID is a universal unique identifier, and that's an ID. We use it a lot in programming. It's a way to give something a label so that you can track it later on. And it is the most powerful concept we have, is to give something a label. It's a username, but guess what? Usernames overlap a lot. There's multiple people named Chris. There's multiple people named, my name also. Usernames aren't great. We need something that is unique, and UUID is unique. It is a long character set. So in my actual implementation, we do have a UUID on here, but we're going to continue and act like that's not there. Issue date is a string. That's when that was issued. Now, but the beauty is now on these systems, we can say JSON schema has a lot of formats built in. We can say, what is the format of this string? Well, it's a date. And specifically, that means in JSON schema language, that means it is a, let me double check. It is a RFD. I think I have it on here. It's like an RFD. I forget the exact number of the RFD. It's like a 3358 or something. It means it follows this RFD specification of how a date should look. And that is amazing because now each implementation system knows, this is a date, but it follows this very specific format. And I need to be able to handle this specific format if I want to interpret this field. And same with expiration date. Expiration date is when the certificate expires, if applicable, right? We have this ability to start defining required fields versus non-required fields. Some certificates don't expire, some do. And so in our data, we want to say if something's required or not. For some reason, I do not have the required fields on this. I think I have it later on. Let's go for it. But so that's our schema on the left, and the data on the right is an example of how this looks in the wild. What does our servers actually deliver? Well, our servers can say title, certificate of buns, issuer, King's Buns Incorporated. The issue date was 2025, March 10th. That is an RFD 33, whatever. I forget the exact RFD.
and an expiration date. So what I've said is that now I'm able to talk about what a certificate looks like in data, and then I have a piece of data that is a certificate that I can validate against our schema. And as I said earlier, I can have guards up front defined to say, hey, you take data, but if the data doesn't match, here's how we can start reasoning about getting it to match so that the rest of our system knows that it's a certificate and what it can do with it. So then we go on to engineer, right? Like, let's say we have an engineer. Now, what is an engineer? Well, an engineer is a Prolog engineer data model. And what do they have? They have a version, because like I said, we know one thing's for sure. We know that an engineer in data might change over time. An engineer has certificates, but they could also have multiple other things. What if we wanted to add job tracking? An engineer now has a job, right? So how do we take an engineer without a job to our new schema of an engineer that has a job elegantly? Well, the elegant way to do that is to say, hey, we realize that engineer is going to change over time, so let's give it a version. And then what that allows us to do is make a version updating system. That allows us to say, if you give me an engineer of version 1, I'll give you back an engineer of version 2. Or if you give me an engineer of version 1, I'll give you back an engineer of the latest version you need, whatever that is. Because I've described how to go from an engineer 1 to an engineer version 2 to an engineer version 2 to a 3, that sort of stuff. And we use this in industry a lot, especially in databases. If you've never heard of Liquibase, Liquibase is a version change CI/CD management system for databases. And it's just a way to say inherently databases change over time. How do we write that out in data? That's like, how do we describe the fact that things change over time, and what do those transformations look like? Because implying the transformations is deadly. You're going to make transformations that just don't work. If you need to jump from a version 1 to a 36, it just is a hard thing to reason about. But if you know how to go from 1 to 2 and 2 to 3 and 3 to 4 and 4 to 5, then you can suddenly just kind of run up your schema changes, and suddenly you're at a version 36. And you get to update your schemas and data models elegantly throughout the whole system. But back to an engineer, they have a version number, and we can even say by default, if they don't specify a version number, they're version number 1, which is fine, because like sometimes you don't need to specify a version number, you just need to define the other things. An engineer also has a UUID property, and that is of format UUID, so that other systems know, like, hey, this is a valid UUID. And then let's say that we can assign them a Discord username or a Twitch username, because like we don't know what platform they're coming to us or registering to us from. So we can take, one or the other. The truth is that we really need one of them, and I'll get to that later. But nonetheless, like a Discord is their username on Discord, and it's a string, and their Twitch is a Twitch username of the engineer, and it's also a string. Well, then we have a certificates array, which is it's really, I think this one's not updated. It's a UUID of a certificate. So you can define that really it's a type string with a reference to a UUID string that is a certificate. But nonetheless, but then we can start saying what's required for a user. Well, required is they have to have a UUID. We can't really have a user without a UUID. However, we also want to accept users from Twitch and Discord, but we need one of them. Like they can't just be this random number floating in space. We need some way to talk to them. So we're going to say they need any of, which any of in JSON schema is saying they need at least one of these things. And one of these things is a Discord property or a Twitch property. So really what I'm saying is I need, for an engineer to be an engineer, I need at least a Discord username or a Twitch username. I don't need both, but I need at least one of them. And the beauty is that I can say that in the data without defining the system at all. All I'm saying here is like, hey, an engineer needs at least a Discord username or at least a Twitch username. Doesn't matter how that looks, they just need at least one of them. And so what that looks like in data is this is me, we have King Buns. He has a Discord, which is King Buns. He has a UUID, which was more than likely automatically generated by the system that created the user. And then what certificates does he have? Well, it's an array of certificates, and certificate is the schema that we went through before this slide, which has a title, an issuer, an issue date, and an expiration date, that sort of stuff. Yes, I am forklift certified. Thank you very much. But that is sort of what our data looks like in our system. So now that we have some data, how do we specify the system itself? And the way that we do that typically nowadays is with open API specification. Now, what that is it is a way to describe API blueprints for humans and machines. And that's a beautiful thing. Like I said, API is application protocol interface. It's a fancy way of saying, like, what does it do? If what is it supposed to do? And that's all I care about. I don't care how it does it. I just care that there's these operations that this system needs to do. And as long as it can do that, I don't care. And so OpenAPI gives us a way to talk about these specifications and the data that these operations work on for both us to read and look at and play with, and for systems to read and work with. It's like I said, behavior contract. Systems need to know, these are the behaviors that I need to implement in order to be a system that works within the contract. And so that's amazing, is to say, as long as you can abide by this contract, you're a system we can use. I don't care what you are, how you work, where you're hosted, who's paying for you. Don't care. As long as you can follow this contract, I will use you. And that's a very powerful thing to have. Let's go back. I went too far. And the best thing about Open API specification is that as of 3.1, we can reference our JSON schema. We have this way to define data, and now this way to define systems in this abstract, beautiful data format, and they can reference each other. They're now allowed to say, like, I'm using this schema and I'm doing this behavior. So if the schema updates, the behavior automatically updates. If the behavior updates, so it's a very modular design system of how we've gotten to now, where we can sort of kind of like keep going and building and iterating. So the last thing is that we have the largest tooling interface of all time these days. JSON schema and Open API specification is dominant in the industry right now. And my example is API Gateway. I can build an entire system in JSON schema and Open API spec and literally import it to my API Gateway in Amazon. And suddenly my implementation is generated. My load balancing is generated. All these questions that curse DevOps for ages. They had to deal with, I need a Kubernetes cluster and a load balancer that would suddenly, automatically distribute across my clusters of each implementation of a container and load balance on that. It's like, I've now gotten to wash that all away. I don't care. I get to describe how the system works, and then I get to tell AWS, hey, here's how the system works, make it work. And it'll do that. And that is where we get these benefits of these contracts. Because if you can define the contract, well, now suddenly any system that's able to interpret the contract can help you implement the contract. Now, don't get me wrong, it's not going to do it 100% for you. At the end of the day, we're still engineers. We still build systems. But if you can reason about that contract and help other people get you to that end goal implementation, they will help you. And that's an amazing thing of tooling that we have with these sort of systems these days. So I went ahead and generated, and I'm going to have these in the references at the end. There's a GitHub with all of this stuff. I described what we would need for this system. We would need an engineer management API. And that would be a cross-platform agnostic API that can say, I need to list all certificates. I need to get a certificate by its UUID. I need to create a new engineer. I need to get all engineers that we have. I need to get a specific engineer by a UUID. I need to add a certificate to an engineer by UU. I need to, and because of that, I was able to implement all of that in data But what that really means is that I was able to take, sorry, that's the wrong one. Let's go to the end. Right, I wrote this data contract, and look at this. This interactive, swagger was automatically generated that knows based on my data, give me all certificates, and it will give me all certificates, and this is what all certificates will look like. It'll look like an array of objects with a UUID, a title, an issuer, an issue date, and an expiration date, It will tell me exactly, and later on you can start playing with it live and poking the system and seeing how it interacts. You can really generate half of your system only by describing what the system looks like and what it does. And even down here you can see in schemas, right? Oh, a certificate has a UUID, which is an abstract certificate that engineers can earn, and it's a unique identifier for the certificate, and a title. And so all these systems now suddenly have this very strict contract that they can use to reason about data. And that allows you to generate UML diagrams, architecture diagrams. I do that on our production thing. I write the schema, and then when I send it to somebody, I have a GitHub action that automatically generates the UML diagram. And so I no longer am manually writing UML diagrams. They're generated. I just wrote the contract, and the UML follows the contract. The API Swagger follows the contract. All the systems follow the contract. If I need to update the contract, I update it, and then all my other systems are now reactive, and they take in the updates because they follow the contract. All the other systems have to do is say, I'm following this contract. And the beauty of that means that when the contract updates, you can make all the other systems reactive and update to follow the contract. And no longer are you dealing with actual specifics. So now we get to the fun part, is that now that we've described our literal implementation, we've defined our contracts, right? We've described how these systems work in the abstract. We went from design. We went from what Sending Grounds was saying. We have a problem. We need to figure out how we implement that, right? Now we've written what implementing that means, right? We've written down how implementing that needs to work. But what we haven't done is actually written that down in code. Up to now, we haven't written any code. And as a senior engineer, I can say writing code is the last step. And that's amazing. You know why? Because we get to generate half of it. We get to say, without AI, we generate all the boilerplate. I get to sit back and say, I get to import it to API Gateway, and it'll fill out the entire API Gateway. And then I just go into each Lambda and fill out the business logic of getting it from the database by UUID, whether that's a SQL query, whether that's a binding, whatever. If I'm writing a more traditional monolithic backend, I get to use Open API Generator, and that is where more specifics will come in. I am going to show a little bit about like how this works in actuality. Open API Generator is a project by the Open API Foundation, and essentially what I get to do is that I get to say, here's my contract, and my contract is going to be implemented in Java Spring Boot. I get to tell the generator, give me the server stubs for Java Spring Boot. And guess what it's going to do? It's going to generate all my types. It's going to generate all my function server stubs. It's going to generate the entire router for the entire application. It's going to automatically generate all of that boilerplate for me. And all that I really need to do is actually be an engineer and implement that logic. And that's insane. I mean, you have generated half of your stuff to follow your contract, to do what you want it to do. And then on the flip side, the people consuming it, your front end, you get to generate those too. You get to generate your clients. If you need a TypeScript client on your front end, if you need a gRPC client on your mobile app that's Android, you get to generate all of those too. And they're going to automatically know what your schema looks like. They're going to automatically know what your data looks like over the wire. They're going to automatically just work. And if you update the contract, well, now you can tie them to GitHub Actions to regenerate the clients with an updating schema way. I'll get into that in a little bit. And they just sort of work, and they can even be selectively opting in on updates if you do like a GitHub action on a specific tag release or something like that. But the beauty of it is that no longer do you have to attempt to align multiple teams. You get to just update the contract in its own repo, and every other team gets to reactively respond because they follow the contract. And as long as they follow the contract, things are going to work, and you get to generate what things are. And that's an amazing superpower that we get to have as engineers nowadays with schemas and with this stuff, is being able to derive actual implementation from contracts. And that's why I said programming languages are disposable. They change over time. Rust is the new hot commodity. Will it be in 10 years? Who knows? I don't care. I'll generate the Rust. Is Java the next big thing? I'll generate Java again. The next big thing is that it comes back around. But, it doesn't really matter to me because they all suck equally. But what doesn't suck is my system. And my system was defined in a language agnostic contract that all of these implementations can be generated from. And that's where we're getting to now, is the ability as software engineers to describe systems and not specific implementation of systems. So with a lot of the API generators now, you get to do like skip overwrite, which is like if an API version changes or something, or you add stuff, you get to keep your old implementations and you can just generate the new stubs for the new implementations. Now, don't get me wrong. If an old implementation changes, it will not generate, because you don't want to lose your old Java, specific database accessors for this get user by UUID. So it won't replace that. You don't want to replace those. You'll still have to manually update those to follow the new contract. However, I do urge. Your API should be changing by version. So if you need to update the old Java data, the old implementation of Java, V1 of the API shouldn't be serving V2 of the contract. You should make a V2 API of Java to serve V2 of the contract. I run into a lot of, people want to have this one system that just magically does everything. And as nice as that sounds, maintaining backwards compatibility for 20 years is horrible. You can really realize that through multiple systems. At a certain point, it fails so hard, upkeeping gets so hard that they just replace it and you make breaking changes. I mean, as even yesterday we were talking about RHEL, Red Hat has made breaking changes on their stuff. It's just going to happen. And the worst thing to do is to really try and support everybody. You can't support everybody. It's not a reasonable expectation. So the best thing to do is to, when you add new things, you add new things. When you change old things, unless you are accepting all the things the old version could do plus more, really what you're doing is rolling out a new version. And the best thing to do is roll out a new version. Roll out a V2 of the API. Don't break everybody else. Don't break your backwards, compatible clients. Keep V1 up, because everybody that built around your system is used to V1. Don't change V1. Don't change V1 to suddenly try and handle V1 plus V2 plus this plus that, because now you're just breaking people, adding more complexity. It's not worth it. Keep V1 working as V1 works. Make a V2, add the new features, add the V2 schema, and move forward. That's the beauty. People that don't want to update don't have to. At the end of the day, you can add a sunset, but that's up to y'all. Just don't break them, keep them, allow them to use V1. You guys move forward, or y'all have moved forward, not you guys, sorry, projecting. Y'all have moved forward, and you made a V2, you added features, you made it better. Congrats, you have a V2. Call it V2. Nobody's going to be upset, make people, if they want to use the new features, they get to upgrade to V2. And that's kind of just how I feel about that one. But you get to generate most of that. So yeah, like I said, this is an example of what this looks like. I took that API thing, I ran it through Open API Generator. I said, give me a Spring Boot Java backend. That's what I said. And it generated all the code. It generated the models, the records in Java. It generated the endpoints. It gave me all the not JDocs, the Java docs on top of the functions. As you can see, it says add certificate to an engineer. It gives me a 201 status code or a 404 status code because that's what I defined in the contract. And all of this was fully generated. And now when you see that one thing where it says return new response entity, HTTP status not implemented, that's the only thing that I get to be an engineer. And I get to take that UUID, I get to add it to the database, write that new record, do it, and return my response I want. Everything else, all the plumbing, all the routing, all the specifics, all the data validation in Spring Boot, it's been done for me because I wrote it down in the contract of how it's supposed to look. And the biggest beauty is that I could regenerate this for Go. I could regenerate this for JavaScript backend. I could regenerate this for a Rust backend. It doesn't matter. All of what you're seeing in that thing is generated. And it's not specific. It's just behavioral. And that contract describes what that behavior is. And we get to generate the rest, and the last thing we need is those, implementation specifics. So I get to be an engineer. I get to actually just write the core logic, which is what I want to do. I want to be an engineer. I want to add it to the database. I want to, do that stuff. I don't want to have to worry about routing and did the user do this perfectly and that sort of stuff. Because if I have to worry about all of that, I'm going to break a lot of things. So that's what you get to do is fill them in. The design is static and the implementation is variable. That contract is that contract. It doesn't matter if Java is implementing it, if API Gateway on Lambda is implementing it, if Golang is implementing it. The contract is the truth. And as long as whoever decides they want to agree with that contract says, I agree with that contract, our system will work. I could swap out our Java backend to a Go backend in a day, and as long as it follows the contract, it will work. Does that work in actuality? No, but that's because they're not following the contract, and I'll tell you that time and time again. So now you get user input or system types. This is sort of like an ad hoc later on. You can start to define schemas for what your internal system expects the schema to be versus what your external system. So sometimes I'll have certificate schema and then user certificate schema. And user certificate schema is like what I actually think a user would enter. Sometimes they won't have an issuer. Sometimes they won't have it, But what I do is I describe a transformation to go from a user certificate to a system certificate. And that allows me to abstractly say, hey, user data's nasty, users input nasty stuff. But for business value, we take nasty stuff. If I don't, the last thing I want to do is prevent a user from placing an order in my e-commerce system. So if that user implements that order wrong as shit, if they implement a false address, a false whatever, I want to recover because I want their money. And so what I'm going to do is I'm going to say, hey, this is a user order payload and it's going to be dirty, but I know how to get to an order payload that the system expects to be clean. So I no longer require my system to expect a dirty payload, but I also allow the user to input a dirty payload, and I know how to get to a clean payload so that the rest of my system gets to operate in that beautiful wonder la la land where everything's beautiful and clean and perfect. So that's sort of like the difference between a user input and a system input type, and you get to describe both and then build transformations between both. Like I said earlier, you get the server stub versus client library. Server stub, they're sort of the ones building out those actual core data implementations. How does a user get added to a database? How does a user get queried from the database? What are the specifics of that for that specific implementation of the contract? And then a client library is somebody that's consuming that contract. They're talking to your server stub. They say, give me all certificates. The server does that, and the client now knows what a certificate looks like, how to reason about a certificate, what data payload it needs to send to the server for a new certificate, that sort of stuff. You sort of get both ends of that spectrum for free, and that's an amazing thing to have. But as of anything, I'm an engineer. I'm a very picky engineer. What are the downsides, right? Like, this sounds amazing in theory, but like anything in theory does have downsides. So let's talk about like what some of those are. Now, the first one is that you have an initial learning investment, right? You need to learn JSON schema. You need to learn Open API spec. Open API spec is traditionally in YAML. If you don't know YAML, you get to now realize and learn what the subset of YAML looks like and that sort of stuff. That takes time. You now need to require your engineers to understand what that looks like and to deal with it. So there is an hour and a monetary number on that learning investment. That is a downside, 100%. And any company needs to realize that, like, yeah, sure, the upsides, in my opinion, outweigh the downsides, but you're going to now have to pay and understand that engineers need to learn how this system works and what that looks like and how they can be proficient within it. So the next thing is that the tooling is still growing and fragmented. One of the biggest things in my own personal example is that I love modular schemas. I love to say that user.schema.json is a file under models, and that certificate is a file under models, and UUID is up a folder in types, and it's a UUID JSON schema. And I love to reference each other relative. And this is something that JSON Schema promoted from the get-go. They used URIs to be able to reference other JSON schemas from a JSON schema. However, in actuality, we got to the point now where it's like the tooling around resolving JSON schema reference URIs is not perfect. It really is not. And actually, this preparing for this conversation, or this, presentation, and even my own work made me realize I should want to be the answer to that. And so I've started working on a Rust-based, agnostic CLI tool for working with these schemas, these API swaggers, to kind of be that I want people to not have to think about it when they're doing this. And I realize that is still a gap. Right now, redoc was replaced OpenAPI CLI, Swagger CLI, which was by OpenAPI. And so a lot of times I build my schemas in modular format, but I bundle them. I use something called a bundler that will take all my schemas and bundle them into one big schema that I can upload somewhere, or generate my types from somewhere. So the tooling, because this sort of industry and infrastructure and type of approach is still so new, the tooling is still ever growing, ever improving. And so sometimes you're going to have to put that engineer hat on, and you're going to have to say, okay, this isn't perfect out of the box, but I can make it perfect for our needs. And so if anybody's interested, you can contact me. I'll show you what that looks like within my own company. That it really looks like a lot of custom GitHub actions. So we have a schema GitHub, and whenever somebody makes an update to that schema GitHub, well, it kicks off GitHub actions. It regenerates the Java types, it regenerates the PHP types, it regenerates the TypeScript types and the Zod schemas, and it does it automatically and pushes to those. And our front end uses a GitHub artifact to reference those types, and so you can pull in whenever you want to update, that sort of stuff. So it can be automated, but out of the box automated is not quite there yet. And I've realized that might be an area that I want to improve. I want to give engineers that ability to have that out of box experience. And so I'm kind of like, figuring out what that means. So you also do have, like I said, the refinement of the development pipeline. If you want to use this in production, industry grade stuff, that's where I created those GitHub actions. Those GitHub actions are different across staging and production. So a lot of my types will automatically go on staging, but production, you really do not want to automatically push things to production. That is a dangerous idea unless you have very good automatic fallback, automatic, that sort of stuff. So production is defined by a tag in Git or a branch in Git. Some places have a production branch in Git, so as things go to that production branch, they'll get rolled out. Sometimes it's a tag, so a version tag. Once the Git commit is version tagged, it'll roll out to production, that sort of stuff. But that still requires somebody that knows Git, somebody that will set up those GitHub actions, that CI/CD pipeline. You don't get that for free, but it's worth it. It's well worthwhile, and I'll be happy to help anybody if they want to get into that. Last thing, cultural friction. We touched on this yesterday in a couple of talks. I deal with a lot of people that are used to working with things as they've known it and as they've learned it. This sort of stuff is new. It is ultra modern. It's probably going to change, but I think this is the best that we know to build data-oriented scalable systems. And because of that, you're going to deal with people that just aren't used to it. And because they're not used to it, and because the way that they've done it has worked for them for the last 10 years, they might be against it, and that is a downside. You're going to have to be the one to, attempt to show them, hey, this is why I think it's better. Here's the flexibility we get, and you're going to have to get that buy-in sometimes. And that's okay, And sometimes they won't buy in, It's just a matter of kind of understanding what the situation and the outlook forecast looks like for your current situation and forecast within your company, and understanding how you can make the best impact that you can given the certain circumstances. But it is a thing. It is a downside. Cultural friction does exist, and you get to deal with it. And so that's one other thing. And the last is that you get what you give. And unfortunately, this is really hard across multiple teams. If you have one team that goes in and changes their types and it no longer aligns with the contract, and then stuff happens, you now have teams that are disaligned. You have to agree and get other buy-in from other teams and other consumers that the contract is the source of truth, because the moment people stop obeying the contract is the moment you get one-off implementations that no longer can scale to another one. You start getting this one says this or sends this that doesn't obey the schema, and now this other system breaks. It really is a you get what you give type of situation where you have to agree that we're all going to follow this standardized contract, and that's going to be our source of truth. And if we have opposition, or if we want to make change, then we're going to get together and we're going to figure out where the contract is wrong or what we need to add to the contract instead of the system, because the system is only a side effect byproduct of the contract. Systems have to be viewed as replaceable side effects. They really do, because they're not important. Languages change, system change. Oh my goodness, we no longer can use AWS, we have to go to Azure. Oh my goodness, none of the stuff works on Azure. You have to build for that, that idea. You have to let the contract be the contract, and you can't rely on specifics. So if you do that, you will benefit. But if you do not, you will be shot in the foot 12 ways from Sunday. And so that's what I mean by you get what you give. You have to agree that we're all following a contract. Now, my last closing message really with any of this is that the only way you're going to get better at any of this, at engineering, at schema-driven development, at programming, is to go create. Go make toy systems. Go create fake implementations for toy systems. Go get them on your GitHub. If you want to be a software engineer, the best thing that they're going to see is that GitHub loaded out with all these fun systems, and they're going to go, wow, this person is an engineer. They know how to create. They know how to design. And on top of you're going to get to the point where you're like, wow, I do know how to create. I do know how to design, because I've done it with all these mock systems, all these toy stuff, whether it's a Discord bot, whether it's a Twitch bot, whether it's a video game mod. Like I said, I started out programming in Minecraft mods in Java. Did I ever expect that me programming Minecraft mods in Java would result in me being, an e-commerce engineer? No. Am I glad that it did? Hell yes. And that's an amazing thing, is that going and creating is what's going to get you to that level where you get to talk without trying. You get to design without trying, is because you've tried and you've done it and you've created and you've built and you've realized and shot yourself in the foot all these times. that you're now at a point now where you're like, I know what I'm doing because I know what I'm not doing. And that is an amazing place to come from. And to me, that has been proven to be the most valuable aspect to my engineering pathway, is to just go engineer. If you want to be a good engineer, the answer is blatantly simple. It's go engineer. And that's what I want to send to anybody, is whether it's software, whether it's sysadmin, whether it's whatever, go do it. I mean, break things, have fun. If it doesn't feel like work, that's even better, because now you're just having fun, breaking things, learning as you go, building cool systems. And one of the things that I think I realized, and I just want to give an example of like my recent engineering journey, I wanted to build more things electronically in the real world. I love real world systems. So specifically, like, soldering systems, Arduino Unos, that sort of stuff. And so one of my favorite sayings is, how do you eat an elephant? One bite at a time. That is the answer. So you go and you start figuring out what that means. And so for me, I had a goal. I said, I want to build my own keyboard, right? So I learned what that looks like. I learned what I needed to buy. I learned the resistors. I learned that I needed Arduino Picos, or sorry, not Picos. I forget exactly the small ones. And so what did I do? I built my own split keyboard, soldered it myself, wired them together. It's a Lily 58. And I did all of that. And all of a sudden, I got to sit back at the end of the day and go, wow. If I told myself I want to build a keyboard and program the QMK firmware myself, I would have paralyzed myself at how complex that is. But if I sat back and said, okay, my goal for today is to figure out what I need to buy. That's all. That's it. Figure out what I need to buy, get it in a shopping cart, and move forward. And then my goal for the next day is to figure out the base plate and get the resistors in. Or figure out what my first step is. And I figured out that was, you need to solder in the resistors for the keycap. Or I'm sorry, for the switches. So I did that. And then like the next one was like, okay, now you need to solder in the switches. Okay, cool. That was just my goal. My goal was like, figure out how to solder in the switches and get them done. After that, it was like, now you have the switches in. Now you can get the Arduinos in to talk to the switches. Okay, how do I do that? Let me Google that, And I kept going, and then all of a sudden, I get to sit back and go, holy crap, I built an entire keyboard and, firmware flashed it myself. And that's amazing. I could have never told myself that I could have done that. And that's not something you should hold yourself to the standard of. But what you should hold yourself to the standard of is, I'm an engineer, and I can get it figured out. And I can go step by step. And at the end of the day, you'll realize that you can eat that elephant. And how do you eat that elephant? One bite at a time. And that is one of the coolest things about engineers, is being able to break systems and problems into subsystems and subproblems, and understanding what that means to you and how you actually get those done. And so the only way you're going to do that is by doing it. And so that's what I want to tell y'all, is go do it. Go find something. Is it video games that you love? Go make a mod. Go find your favorite video game, make a mod. Is it systems that you love? Build a home lab. Build a jump box. Build the things that like you just find intriguing, because all the other slices of that pie are gonna come together. And the best thing you can do is document it, learn, move forward, and then all of a sudden, I promise you, companies will talk to you, will look at your resume, will look at your GitHub and go, oh, that's an engineer. Like, they build things. And that's what they want. They want somebody to solve problems. And if you know how to solve those problems, you'll work. You'll get it done. You'll be valuable to them. And that's just my experience. But obviously, I wanted to share. And so anything else, I wanted to give my resources. I'm going to post these slides. I'll post the link to the whole Google slide thing. There's Google, the JSON schema reference. Schema to Zod. One thing's for sure, two things for certain. You are going to have a front end, and that front end is going to be in JavaScript. That's why I said you get to learn JavaScript as a computer scientist these days, a software engineer, because every PWA, progressive web app, every application have a JavaScript front end. You don't get to get around the fact that you're going to have JavaScript somewhere. Zod is the #1 right now on top of TypeScript. TypeScripts are for types. Zod is for type generation and TypeScript and runtime validation. So I'm going to link the tool that generates all that stuff from the JSON scheme of the Open API. Read.Docly is the CLI that I use for all my stuff. Read.Docly is they have an enterprise edition, stuff, but they also have CLI, free to use community. That's how I bundle my schemas together. That's how I bundle my Swagger together. If I need to go from JSON to YAML to TOML to whatever, Read.Docly is going to be my answer. It's the #1 commonly used. Open API Generator, that's the tool that you use at the end of the day. Once I run my stuff through Read.Docly and generate my one big file, I bundle it into one big file. I then take it to an Open API Generator and I say, give me the Java backend, give me the TypeScript front end, give me the Go backend, give me all this stuff. And it will generate all those server stubs, all those client libraries. Hammett-driven development, that's the thing I mentioned earlier where it's a keynote by Rich Hickey, the creator of Clojure. That's where they go through the ideals of you're much better off spending your time in design than implementation. So if you take the time and spend 4 hours creating the idea of how the system works, you're going to be paid tenfold because you're going to have 10x less code. You're not fleshing it out in code and making realizations as you build the system. You're making the realizations and simplification before you ever build the system. And there's a superpower to that, I promise. And the last is that the GitHub that I have for the engineer models, the Open API Swagger and stuff that I did compile with Read.Docly, that's on GitHub. I'm going to link everybody to it. I wish I had more time to go fully through a demo session, but I'm already approaching 2 hours, so I'm going to call it on that one. And then lastly, I just want to give anything, if anybody has any open discussion of questions for a software engineer that cares way too much about programming, that is too much of a nerd, I'd be happy to answer them and give my best opinion on that. But other than that, that is the main contract first. Once you have the contract, things will come, I promise. So thank you very much. I appreciate you all. I'm still just a 25-year-old engineer trying my best, so thank you.